In this video, we will be solving question number 54 from GATE 2020 chemistry paper. Now the question is the following. For the ring opening reaction of cyclopropane to propane at 25 degrees centigrade, the pre-exponential factor is 4.3 times 10 to the power 15 second inverse. Now we have to find the entropy of activation for this reaction in the unit Joule Kelvin inverse mole inverse. Now the value of Planck constant, which is H, is given 6.626 times 10 to the power minus 34 joule second, and the Boltzmann constant is also given, which is 1.38 times 10 to the power 23 joule Kelvin inverse, and the value of universal gas constant R is also given 8.314 joule Kelvin inverse mole inverse. Now let's say or assume a simple bimolecular reaction A plus B to C. Here A and B are the reactants and C is the product. And in transition state theory, we actually assume that the reactant molecules, that means A and B, will form or will react an activated complex, what we call transition state, and then this activated complex transform into product. So first A and B will react to form AB double dagger, that means which is the activated complex, and then this activated complex will transform to product P. And in TST or transition state theory, we actually assume that there is an quasi equilibrium between the activated complex, that means AB double dagger, and the reactant molecules A and B. So there is an equilibrium between the activated complex and the reactant molecules, and let's say the equilibrium constant for this reaction is K double dagger. So from thermodynamics, we can write down the expression of K double dagger. So K double dagger will be just the concentration of the activated complex divided by the product of concentration of reactant molecules, that means concentration of A times concentration of B. So this is the expression of K double dagger, which is the equilibrium constant for this reaction. Now the rate of the reaction of the product formation, that means from activated complex AB double dagger to product formation. For this reaction, the rate of the reaction will be dP dt equal to some rate constant Kp, let's say, multiplied by concentration of activated complex, that means AB double dagger. Now from this relation, we can find out what is the expression of concentration of AB double dagger. So AB double dagger will be K double dagger times concentration of A times concentration of B. Now we can put the expression of AB double dagger, that means this expression here. So dP dt will be Kp times K double dagger times concentration of A times concentration of B. Let's say Kp times K double dagger equal to K. So this is the rate constant for the overall reaction, that means A plus B to C. So total dP dt, that means dP dt will be K times A times B. So here K equal to Kp times K double dagger, and from statistical mechanics we can write down the expression of Kp. So K, the total expression will be K equal to Kbt divided by H times K dagger, where Kb is the Boltzmann constant, T is the absolute temperature, H is the Planck constant. So this is the expression of rate constant K. Now we know that the K double dagger is the equilibrium constant for this step. Now from thermodynamics, we know that the equilibrium constant K equal to e to the power minus delta G double dagger divided by RT. So delta G double dagger is the change in free energy of activation. That means this is the activation free energy for this step. And so delta G double dagger will be delta H double dagger minus T delta S double dagger. So we can put this expression here. So K double dagger will be exponential minus delta H double dagger minus T delta S double dagger divided by RT. So our K is KBT divided by H, K double dagger. Now we can put this expression of K double dagger here. So K equal to KBT divided by H e to the power minus delta S double dagger divided by R times e to the power minus delta H double dagger divided by RT. Now we know the relationship between the activation energy EA and in enthalpy of activation delta H double dagger. Let's say the reaction profile of energy profile for this reaction looks like this. Let's say this is energy, y-axis is the energy, x-axis is the some kind of reaction coordinate. Here this is the reactant molecule, that means A plus B, and this is the product, let's say P or C in our case, and this is the reaction profile. So activation energy is, and this is the activated complex or transition state. So activation energy is energy difference between these two states, reactant molecules and the activated complex. So this is activation energy EA. So the relationship between the activation energy and in enthalpy of activation is this: EA equal to enthalpy of activation plus R times T. Now we can put the expression of delta H double dagger from this expression into here. So let's put this. So K will be equal to KBT divided by H e to the power delta S double dagger by R exponential minus EA minus RT divided by RT. So let's combine all these and write down K equal to A times e to the power minus EA divided by RT. So all this expression apart from activation energy divided this part are put in the expression of A. So in the last slide we have seen K equal to A times e to the power minus EA by RT, and the expression of A is this: KBT divided by H e to the power minus delta S double dagger divided by R plus 1. Now A is called pre-exponential factor. Because the term A is appearing before this exponential term, that's why it is called pre-exponential factor. Now from this expression we can find out the expression of delta S double dagger, that means entropy of activation for this reaction A plus B to AB double dagger. So entropy of activation will be R times ln, so bracket, first bracket will be this. So delta H double dagger will be R times ln in E base AH divided by KBT minus 1. So let's put all these values. So delta S double dagger will be 8.314 times ln AH by KBT, that means 4.3 times 10 to the power 15 times 6.626 times 10 to the power minus 34. KB means 1.38 into 10 to the power minus 23, and T is the 298 Kelvin minus 1. So the delta H dagger will be 46.499, and after rounded up in up to 2 decimal places it will be 46.60. The unit will be Joule Kelvin inverse mole inverse. So the answer of this question, that means the value of the entropy of activation for the reaction cyclopropane to propane will be 46.60 Joule Kelvin inverse mole inverse. Now for further details on this topic you can visit the following NPTEL lecture series on the topic of chemical kinetics and transition state theory. Instructor is Professor Ambar Jain from IIT Bombay. Thank you.